Hello everyone. So welcome to our week 5 practice problems. So we are now in problem number 3, sum of two independent continuous random variables. Consider two independent random variables x and y whose PDFs are as follows, where a and b is greater than 0. Okay, so determine the PDF of W is equal to x plus y. So like the problem previously, we are going to take the convolution of these two probability distribution function. But the only difference here is that these two random variables are now continuous. This random variable x is a uniform distribution function. This is uniform distribution. Okay. And the second one is an exponential distribution. Okay. So that we can imagine what these two signals are like. So let me just draw it. This is the probability distribution function of x. So we have here from 0 to a, the height here is 1 over a, and the probability distribution function of y is an exponential function. So this one is, the height is b. So because b e to the negative b times y. So to do this, we are getting the convolution, the continuous convolution of these two functions. Okay. So there are 4 steps to do the continuous convolution. That is to flip, shift, multiply, and integrate. Okay. So we start with flipping. So we choose a specific signal from these two that we are going to flip. Okay. So we are taking, so for example, since this is the easier signal to flip, okay, we flip the uniform distribution function. So what we are going to get is parameter x. This one is f sub x of negative x. So it is already flipped. Flip with respect to the y-axis. So this one is 0. This one is negative a. Okay. And then the next step is to shift by z. Okay. And then we have here certain intervals wherein we're going to see if there is overlap between the two signals. So for example, when the amount of shift is less than 0, okay, what can we say about so let us now sketch the both distribution on the axis y. So this one here is the exponential distribution. This one is f sub y of y equal to be to the negative b times y. And then we have here also the probability distribution of x, wherein this one is 0 plus z and negative a plus z. And since z is less than 0, therefore we are moving along from negative infinity, okay, we are shifting it until the point wherein this edge here coincides with the edge here. And since, okay, so since we shift it by this value, and then the next step here is to multiply both functions with each other and then to integrate. But then since there is no overlap, therefore this function f sub y of y multiplied by f sub y of z minus x is equal to 0. Therefore, our probability distribution function is equal to 0 whenever z is less than 0 because there is no overlap between the two. So now we move for the interval wherein there is an overlap between the two. So we will obtain a specific probability distribution function. So for instance, when z is between 0 and a, So what can we obtain, or how can we sketch the 2 in y? So we have here be to the negative by, and then we have here the uniform distribution function, where this one is equal to, again, this is z, and then this is z minus a. So that is always the case, no? If we have, the original is 0 and a, and then we just add the amount of shift, so z. And so you could just imagine, when z is between 0 and a, this is the case wherein this right edge here now penetrates this edge here, but this left edge here is still not coinciding with this edge here. Can you imagine it? So that is the case wherein the amount of shift is between 0 and a. So what I want to do, so to further visualize or to help us in solving this integral, we specify specific regions wherein there are changes. So for example, the region 1, okay, so f sub z of z is equal to integral from negative infinity to infinity of the product of the two functions. But for each region, each of the function changes. So for example, here in region 1, the integral is from negative infinity to this parameter z minus a, and then we multiply the value of the function at that interval. So in this case, the probability distribution function of y at this region is equal to 0, and the probability distribution of this function of x at this interval is 0 integrated over y. So this is region 1, and we know this to be 0, obviously, right? And then we add all the regions here. So for the next region, region 2, the integral is from z minus a. Okay, so take note of the region here, from z minus a to 0 here. Okay, until the point wherein the function of y changes. So because the function of the probability distribution of y changes from 0 to this value, to the exponential. So we have here the probability distribution function of y is still 0 at this region. Okay, this is still 0 at this region, but the probability distribution function of x at this region is now 1 over a integrated over y. So that is still 0. But we all know, okay, so this is from z minus a to 0, that the region of overlap between the two is only at region 3. So that is the integral from so this is the region integrated from 0 to z. So this is from 0 to z. And we know that the function, okay, the value of the function of y at this region is this exponential value, which is expressed as a exponential function, be to the negative by multiplied by 1 over a dy. And for completion, we just integrate also from the region 4, from z to positive infinity, z to infinity. So the value of y is still be to the negative by, but the value of x is now 0 dy. So this is region 4. We know region 4, region 2, and region 1 to be 0 just by observing this sketch. So we just obtain the integral of this parameter. So to do that, let me just write that fz from 0 to z 1 over a be to the negative by dy. So b over a is a constant, and then the integral of e to the negative by is e to the negative by over negative b, evaluated from y is 0 to y is z. So what we will get here is 1 over a times 1 over, because we cancel this, okay, 1 over a negative e to the negative b z, okay, minus negative e to the negative b times 0. Or, to simplify this further, 1 over a times 1 minus e to the negative b z. This is the case wherein our z is from 0 to a. Okay? Now, the final interval or the region of interest is when z is greater than a. Okay? So, the sketch now here is y. This is still the exponential function be to the negative by. Okay? And then, okay, just imagine again with me z and z minus a. When the amount of shift is greater than a, the right edge here now exceeds or penetrates this edge here. So again, you could specify specific regions here of interest 1, 2, 3, 4. But since we are only interested in the region of overlap between the two, we just focus on this region. Okay, so f sub z of z is equal to the integral from z minus a to z of the value of f sub y at that specific region, which is be to the negative by, times the value of x, the probability distribution function of x at that specific region is 1 over a, integrated over y. So again, this is just as an integration. So once again, this is equal to b over a times e to the negative by over negative b, integrated from y is z minus a to y is z. Okay, so cancel. We have here 1 over a negative e to the negative b times z minus negative e to the negative b z minus a. And finally, we have 1 over a times e to the negative b z minus a minus e to the negative b z, wherein our function here is from z to z is greater than equal to a. So if we are to complete our probability distribution function, we will now obtain a piecewise function wherein we get this specific expression. So f sub z of z is equal to 1 over a times 1 minus e to the negative bz when z is between 0 and a, and 1 over a times e to the negative b z minus a minus e to the negative bz when z is greater than a, okay, and 0 otherwise. So that is how you solve this kind of problem, okay, and that is how you do continuous convolution. So thank you for listening and see you on the next problem.